So let me recall some of the points we tried to make last time. So we essentially showed that we have sufficiently many divisors. We could produce logarithmic forms. And of particular importance for the last part of the talk was in the situation where we had two hypersurfaces, H1 and H2, such that the difference had zero-Chern class. So here I mean, of course, that this is perhaps the Chern class of the associated line bundle. And then in this situation, we show that we could produce omega logarithmic one form with residue divisor equal to d1 minus d2 and periods of omega contained in IR. Perhaps I was too fast when I did this construction. Let me just repeat it in perhaps more concrete terms so that we don't get lost in what follows. So let's say that I have here X, my compact Keller manifold. And I have this, these divisors H1 and H2. Hypersurfaces. Next. Okay, and let's assume that they satisfy this condition. So concretely, this means that I can produce a function, or I can get a covering of X by open sets. And I can get meromorphic functions on these open sets. Such that they differ on the intersections by lambda ig, which is a complex number. In general, if I just take any divisor, we have these transition functions are just functions, holomorphic functions, nowhere vanishing. But in this case, since we are on a compact Keller manifold and we are assuming that CQ equals 0, I can choose these transition functions. So Fi 0 minus Fi infinity will be H1 minus H2 intersection y. And I can choose these transition functions in S1. Okay? And so we get this picture, so H1, H2. It's not really important if they are disjoint or not. It's important in applications, but let's just draw them disjoint. And then we have this function, so this will be Fi equals 0, Fi equal infinity. And since we are able to do this construction, we can do two things here. Since this guy takes value in S1, we can define a function, a global real analytic function f, which is just the modulus of fi, which will go from x to 0 infinity. And we can also take the logarithmic derivative to produce this form omega, which will have these properties. So the fact that the periods are contained in IR is exactly the fact that these transition functions are in S1. And so we are in this situation. So these are the level sets of this big function f. And we have this. Okay, I want to recall that because I would like today to try to address the following question. So we saw last time that when we had two disjoint hypersurfaces with proportional Chern classes, when we had three of them, disjoint hypersurface with proportional Chern classes, we were able to produce a fibration. And the key to produce this fibration in at least one of the arguments was to look at this foliation, the foliation defined by this form omega. And so I would like to address the question today, what can we do when we have only one surface or hypersurface? Okay, so of course, since there is only one, I want to assume that it has numerically trivial normal bundle, or even perhaps trivial normal bundle, and ask, can we produce a foliation similar to the one that we produced here using global properties of compact Kähler manifolds? Okay, and so this is somehow the subject of a very beautiful theory due to Weda. So the basic question is the following. So let's assume that now I have y contained in U. Let's say that y is compact Kähler manifold. And U is just an open, it's a germ of complex manifold containing Y as an hypersurface. And Weda asked exactly this question. When can we produce a logarithmic one form, a closed logarithmic one form on U, such that all the periods are purely imaginary, and the residue divisor is exactly the hypersurface Y. So, basic question. When there exists closed logarithmic one form with purely imaginary residues and residue divisor equal to Y. And the natural setup to do this, one natural way to do this, is to do the following. So if you think about it, just from what we made here, if we have a differential of that form, when we took the exponential of local primitives here, you are going to get a function defining your divisor. And the fact that we have purely imaginary periods means that when we integrate this function, we are going to have this relation. So we want to find functions defining my divisors Fy, which will satisfy this condition. And then the lambda ij is just a cocycle for the normal bundle of Y. So of course, here we have to assume that the first Chern class of the normal bundle of Y is 0 in order to have these conditions, because that's what we get from that. Okay? Very good. And so a way to formalize this problem and to transform the problem in a problem of formal geometry is to consider the following. So we can assume that U is a very small neighborhood. It's just a germ of complex manifolds. So we can assume that U and Y share the same homotopy type. So if I have that the normal bundle of Y has 0 Chern class, it carries a metric, a unitary fat metric. So we have this, this connection on U, and I can extend it topologically to U, since they have the same homotopy type. It's just topological data, since it's a flat connection. So we have this connection on U. So I have this. I can extend the normal bundle of Y to something we call the normal bundle of Y on U. So it's a flat line bundle on U. And we can also extend the normal bundle of Y in the usual way as OU of Y. And then we consider U, the line bundle, which is n tilde Y tensor OU. And if you think a bit, if you want an exercise, the existence of this collection of functions satisfying this kind of relation is exactly to say that U, so the answer to the basic question is yes, if and only if U restricted, or U is trivial. Isto é, aí, this U is just OU. Okay? And so what Ueda proposes, well, let's look at this line bundle at successive infinitesimal neighborhoods of Y inside U. So profiting from the notation which was already introduced by Jean-Benoit, I will use a notation slightly different, but we have these successive infinitesimal neighborhoods. I think that's what Benoit called Y subindices. And this will converge to the formal neighborhood of Y, which I will denote by calligraphic Y. So this is the formal neighborhood of Y on X. Usually people write keep X in the notation, but I think this is just a fattening of Y, so I prefer to keep Y there.
X is U?
U, yeah, X is U. Okay. And if you want to decide this guy will be trivial, we can ask for several different questions. We can ask if U restricted to this formal neighborhood is trivial, or even we can look at U at this preliminary neighborhoods and in this finite neighborhoods. So we define the following as the Ueda type of Y. It will be two things. It will be infinity if U restricted to Y is trivial, or it will be K if U restricted to Y K is trivial, but U restricted to Y K plus 1 is not. Okay. Very good. So this seems a very fancy way of saying things, but at the end of the day, it's something very, very concrete. So, as I said, this condition here is equivalent that we have formal functions, fi, defining y, which relates by lambda ij through complex number of modulus 1. And this condition is equivalent to say that fi hat is equal to lambda ij plus fj, you can choose, or fj to the power k a, or let's go u ij fj, where this guy I will give now a cohomological meaning. Which we can figure out by just seeing how the transition function works, but I will just do the general nonsense and see what we are trying to do. So we have the Poincaré group of y k plus 1, which is just h1 yk plus 1 O star yk plus 1. We have the restriction morphism to the Poincaré group of yk. And here we have this truncated exponential sequence, which maps by computations very similar from what Jean-Benoit did one day ago. Here will be the normal bundle of y over normal bundle of y. I think it's k, tensor k plus 1. And so you see, we will be with Weda type equal to k when I have a class here, a map, a guy here, the image of u here is trivial. So I'm having this guy being mapped to the trivial line bundle. And so what we get here, it's a class, a cohomology class here. And this cohomology class is exactly the uij. There is no quotient where? Here?
Yeah.
Oh, yeah. Yeah, thank you. Oh, yeah, I was mixing up notations. Yeah, sorry. And so the guys that appears here is the Uij. Very good. And so why is this interesting? So there is this following theorem by Ueda. Oh, and the first result is not actually due to Ueda, even if the definition of this invariance is due to him, but I think that it already appears in work by Hirschowitz and perhaps somebody else before the work of Ueda, and says the following: if the normal bundle of Y is torsion, and U type of Y is equal to infinity, then there exists, not only exists this foliation, but in this case, since the torsion, the normal bundle is torsion, this complex numbers are root of the unities, and there is not only a foliation, but there exists a non-constant holomorphic map, perhaps after restricting to a smaller neighborhood. The pullback of 0 is the order times Y. And so this is the result which is proved, can be proved using this. First you prove that there exists a form of vibration, which is essentially by definition, and then you prove that the convergence using arcing approximation theorem, but or Grothendieck's comparison, I don't know. And the really new thing here, and the really new phenomena here discovered by Ueda, you have to assume that Y is a curve, so dimension of Y is 1. And U type of Y is finite. Then there exists a system of pseudo-concave neighborhoods of Y. I will pretend that I understand what that means, and we'll just say a consequence of that from the theorem of Andreotti. This is a theorem of Andreotti, which I was already mentioned by Jean Benoit also. And this implies that the transcendence degree over C of the field of meromorphic functions on U, or the germs of meromorphic functions on U along Y, is at most 2, the dimension of U. Okay. So the proof is it's a very nice piece of analysis. He constructs a pure subharmonic exhaustion of the complement of Y in U, but I don't want to get into the details. I thought of remember this result and explain it here because it makes a very good counterpoint to these formal methods. This is one instance where the formal and the convergence theory are completely different. So there's a theorem by Hironaka and Matsumura who says that in this situation, the field of formal meromorphic functions along Y has infinite transcendence degree over C. So you have much, much more formal meromorphic functions than holomorphic functions. And the proof of this Hironaka-Matsumura, it's exactly using exactly the same arguments that Jean-Benoit have done 2 days ago. And so here is something that the formal methods do not see, but the analysis see. I think it's very, very interesting, and I think deserve to be better understood. Very good. But then what? Why am I recalling this? Because I want to state a theorem which is due to Clodon, Loré, myself, and Touzé, which somehow answer this question. Well, no, does not answer this question, but answer somehow different question. So if we want to look for logarithmic forms, so we see the way that shows that in general there is no hope. There are obstructions to do that. But can we dream that in this situation where we have this kind of condition, can we dream that there will exist some canonically associated foliation? Perhaps in the local situation or in the global situation, but here we can say something in the global case. So now let X be compact scalar. O is a manifold. And Y contained in X, a smooth hypersurface. Smooth and connected, of course. Unfortunately, we cannot prove the most general case, but let's assume that the normal bundle, if the normal bundle of Y is torsion of order K, and U-type of Weyra of Y is greater than K, then there exists a canonically a foliation on X having Y as canonical as a compact leaf, so no singularities on Y, and which is moreover canonically associated to canonically associated to the situation, right? The Y. To be fair, we should also add here, there is an important part of this result, even the suggestion that this result should be true. It appears in the result of in the work of Niemann. And let me give a proof of this result, because it's very much in the spirit of what we have done before. And I will just comment what I will make a more precise statement at the end. I will comment what Niemann did and how it appears there. Okay? Very good. So the proof is really, really simple. It's just to look at this equation sufficiently hard. Okay? So I'm taking fi as the defining functions of y, right? And I'm assuming that the order is k and the normal bundle is k. So let's just, instead of looking at fi, let's look at fi to the power k. So if we look fi to the power k, we will see that this lambda ij will become 1, because they are kth root of the unity. And here, what will appear, since the U type is at least k, I can also write this as fjk times uij times fjk. Okay? But the nice thing is that since this k is appearing here, when I look at the reciprocal of fi, I get that 1 over fi to the power k minus 1 over fj to the power k is just, let's call vij, is holomorphic. And clearly defines a class in H1 X OX. Right? We need this power k here because we are taking the inverse and then to counterbalance with this 1 over fjk. And then we have two things to do. Essentially, if we see the way that we define it, so we have that this fij, or at least k times it, modulo some non-natural isomorphism. This guy will be the Weda class, the kth Weda class of y. Understanding the kth Weda class has this element here. In case U type of y is equal to k. If this is not equal to k, then it must be 0 on y, on restriction to y. So if U type of y is greater than k, then this class, Vij, belongs to the kernel of the restriction morphism. Right, by the definition of the Weda type. And we have saw last time in the very end that in this situation, y is a fiber of the fibration. In this case, of fibration. And this is the canonically associated foliation. So, and this is the Niemann result. He proved differently, but he proved that if the normal bundles has order k, and the Weda type is order greater than k, then y is fiber of a fibration. Now we want to construct a foliation from this thing. Very good. So what do we do? Well, if you don't know what you do, you take derivatives, right? And so we get that this guy will be equal to this guy. And then I get this d of vij, which is an element in H1x omega 1x. But we are in the Keller world, so the Fourier spectral sequence degenerates at U1. And so this guy, I can write, this class is 0, right? And so this thing can be written as alpha I minus alpha j. Then we can just rearrange things. To produce a global holomorphic one form. And we can also resolve this cocycle using DD bar lemma, but I don't want to get into the details. We can assume that this alpha I is also 0. And so I can construct this one form theta, or omega, I don't know, which will be a closed one form. Closed one form with poles of order k plus 1 along y and without residues. Okay. Well, this one form is not canonically attached to the foliation, to the situation, because there is still some ambiguity in its definition. So here when resolve this cocycle, we choose this closed one forms. We can always add, so this is well-defined only modulo H0 x omega 1x. And in order to have something which is more canonical, you can do the following. You can assume that the periods to normalize, to kill ambiguity, we can choose alpha I such that the periods of omega restricted to U, a neighborhood of Y, is the periods of an anti-holomorphic one form. You see, because we construct, so this will be essentially the component come from this element in H1O. Yeah, I said something which is not exactly true. Oh, no, it's true, yeah. Is that the foliation is canonically attached. The one form is not, because it can always multiply by C star. But besides multiplication by C star, this is the one form. And so the foliation is canonically attached to our situation. Okay, so here we have again the situation, right? Somehow in last time we start with a bunch of divisors, and we could cook up logarithmic one forms out of them, foliations out of them, and in some situations these things were canonically attached to them. For instance, in the case where we have 3 disjoint divisors. And here again, we now have only one, but with this kind of strong assumption, we can produce a canonically attached foliation. Notice that if we are ready to assume if we are proving that if ny is O1, OY, then the theorem says that either you have a fibration or this closed one form, closed rational or meromorphic one form. Okay? Very good. So why I want to say that, because I would like to somehow discuss and try to show how to apply this to some natural problems in formal geometry, which is the problem of the formal principle. Trying to connect with the talks of Jean Benoit. So what is this formal principle? So let's try to formulate, to look it in the simplest case. Suppose that I have a curve. Oh, let's keep the same notation. So y, a hypersurface, or even a subvariety in variety U. So let's assume that I have y1 in U1, y2 in U2. So this is a compact subvariety of a complex variety. Again, the same situation. And we can, from this data, look at the formal completion of one and the formal completion of the other. Formal completion of y inside U1 and formal completion of y2 inside U2. And you have this situation. And you can assume that these things are formally isomorphic. Okay? And so, one natural question, and that's, we say that this pair U1, Y1 satisfies the formal principle if for any U2, Y2 such that Y1, the formal completion, we have isomorphic formal completions, then there exists isomorphism between the germs. Okay? And I'd like to make a point of how is the situation in the case of surfaces, where I look, y1 is a curve, so if I have a C germ of compact, of smooth, compact curve on a surface, let's call surface U. And so here the situation is pretty clear when C square is negative. So this is the theorem of, I think, Grauert. Says that C satisfies the formal principle. The situation when the square is positive, then this is this theorem by, I don't know who proved this first, but this is, C satisfies something even stronger. Somehow it's related to this result of Andreotti. It satisfies the, let's call it, strong formal principle, which we say that not that exists another isomorphism, but that your formal guy was already convergent from the beginning, right? Just like in the case, the question of algebraization. So it's formal is indeed convergent. And the situation of square zero is very interesting. So things start to be really strange is in the case of C square equals 0. So when C square equals 0, it's essentially, it almost never satisfies the formal principle. Essentially, it will satisfy the formal principle, stated in that way, only when C is a fiber of a fibration. Well, that's not exactly true. But let me say what we know about that. So there is the first example of that is an example due to Arnold, which also used and comes from foliations, right? So you take an automorphism of C0 with this guy different with norm 1, but not root of unity. So the eigenvalue at that 0, it's infinite order. And with infinitely many periodic points. And then you construct U as a suspension of pi 1 of C in Z, where you send 1 to this guy. Right? So this is this construction where you have a curve and you produce a foliation transverse to a fibration with this first return map. Of course, it's not a first return map, it's with this holonomy. And so this thing is something which is formally equivalent to a neighborhood of the zero section of the normal bundle with this representation, but it's not, there is no convergent automorphism. The fact that there is no convergent automorphism essentially follows from the fact of this existence of infinitely many periodic points, because they give rise to infinitely many curves inside this neighborhood, and also this is this holonomy is not linearizable. So this is the situation with this is an example with non-torsion line bundle, normal bundle. And you could, perhaps when the normal bundle is trivial, would be luckier. But no, there is recent work by Loret, Touzet, Ton, c'est ça? Non, Loret, Ton, Touzet. Lohay-Ton-Touzé, which essentially shows if the normal bundle of C is trivial. There are, so let's, you can look at the paper, but let's just state like this. There are examples of infinite dimensional families of surfaces, of germs of surfaces, containing C with a normal bundle of C trivial, with fixed formal type, but 2 by 2 non-analytically equivalent. And so somehow this question seems completely hopeless, even in the simplest case. But one amusing consequence of this result, that the simple result that I proved, that I showed to you, is the following result. Which we have just found. Now Olivier is doing a postdoc at IMPA since last year. And the results the following. So if we have, let S1, C1, and S2, C2, be 2 pairs of projective surfaces, projective curves on curves, such that the normal bundle of C1 is equal to OC1, and the formal completion of S along C1 is the formal completion to S2 along C2. So instead of taking these local things, I'm now assuming that these curves are contained in projective surfaces. We are in the global setup. And so I'm assuming that this global data, they coincide, they are isomorphic, they are formally isomorphically on the formal neighborhood of C1 and C2. And also assuming this. Then, either C1 is a fiber of a fibration, or S1 is birational to S2. So the formal type, except in the case of fibrations, does not only determine the local conversion type, but determines the birational class of the surface, the birational equivalence class of the surface. Any question? Okay, so the proof is really simple. So at least the idea of the proof. So we already had one closed one. From this situation, this setup, I can apply the theorem that I stated, and I just erased, which says that we have this closed rational one form canonically, or this foliation canonically attached to the situation. And then if I have a formal equivalence between these two things, it will preserve the corresponding foliations. But now this foliation, how it was produced? It was produced from the divisor, the curve C1, and a class in H1O. So this class in H1O can be represented by an anti-holomorphic one form. So my automorphism, this formal map, will not only preserve the foliation that I just constructed, but also will preserve the multiples of this holomorphic one form, of the anti-holomorphic one form. So assume C1 is not a fiber. So then we produce two things. One, it's this closed rational one form. With poles with, it's called 2C1. And we can also produce we have this class, the Weda. We have this class, we have a class in H1, S1, OS1, which I can represent by anti-holomorphic form. One form, and restricts to Y1 to the Weda class of Y, of C. And so these two data are preserved by my formal equivalence. There's something intrinsically attached. Not the forms, but rather the vector space generated by these two guys. And the same thing for the other. So when you look, you have a formal map preserving these two things. And then you can, it's not very hard, but you can apply arching approximation theorem. So with some work, but not very hard. Essentially, all these things are exact, and so locally, they are just some work, an arching approximation. Implies that the convergence of a formal isomorphism. And we can use Weda's theorem, which I erased. It was here. I can use Weda's theorem to show that indeed the formal is birational. Yes. The thing which is defined only in a neighborhood of this C1 and C2 can be extended to the whole varieties, and we get birational. Very good. So that's what I planned for today. So in the next time I will change gears. I will talk about something completely different, but still related to invariant curves of by hypersurface, invariant algebraic hypersurface invariant by foliation. But this is somehow that I want to talk to you today.